Assalamu alaikum dear students. I hope you're all fine by the grace of Almighty Allah. I welcome you all to the 26th lecture of Thermodynamics 2. Lecture 26. The contents of lecture 26 are ideal Rankine power cycle, efficiency, actual Rankine power cycle efficiency, losses that are involved in actual Rankine power cycles. So these are three types: turbine loss, pump loss, boiler and condenser loss. We will discuss the method how we can increase the efficiency of a Rankine cycle. Then we will go through some numerical problems and conceptual question answer at the end of the lecture. Ideal Rankine cycle. So in the previous lecture we have already discussed the processes that are involved in the ideal Rankine cycle. So there are four processes. And there are also four components that are the main component of ideal Rankine cycle. So the first one is pump, boiler, third is turbine, and the fourth one is condenser. So this is a cyclic process from process 1 to 2, that is a pump, and this is shown. So 1 to 2, this is a pump. From 2 to 3, this is a boiler. 3 to 4, this is a turbine, and then 4 to 1, this is a condenser. So heat is added into the boiler Q1 and heat is rejected through the condenser, that is Q2. The pump is a work consuming device, so WP amount of work is the pump work that is introduced into the pump, and turbine is a work producing device which produces WT amount of work. So here the temperature, pressure, we talk about temperature T1, P1, H1 are the temperature, pressure and enthalpy values at state 1, and at state 2 the temperature value is T2, pressure is P2 and enthalpy is H2. Pressure as P3, state 3 is P3, H3 and T3, P4, T4 and H4. So two processes are isentropic and two are isobaric process. So P2 is equal to P3 and P4 equals P1, whereas S3 equal S4 and S2 equals S1. So for process 1 to 2, this is isentropic process, and process 3 to 4, this is also an isentropic process. Process 2 to 3 and process 4 to 1 is an isobaric process, therefore the pressure will remain same. And this is the main steady flow energy equation. Heat in plus enthalpy at the inlet plus work input is equal to heat out plus enthalpy at the output plus work extracted from the process. These are the bottom right are the schematic and TS diagram of ideal Rankine cycle. So this is T and this is S diagram, TS diagram. So for process 1 to 2, as you can see, this is isentropic process 1 to 2. This is isentropic compression in a pump. So the pressure as well as temperature will increase. So this is isentropic process. So it is a straight line parallel to y-axis, and these are two constant pressure lines or curves. So as you can remember, in the TS diagram, the constant pressure lines are in the zigzag manner and their trend is in the upward direction. So from for process 1 to 2, this is a straight line isentropic process pump. From process 2 to 3, this is constant pressure heat addition. So the process line will follow the constant pressure curve. So heat will be added, and initially it is in the liquid phase. As the heat is added, so it will move to the saturated liquid. More amount of heat is added, then this is the phase change process from saturated liquid to saturated vapor. And at state 3, the working fluid is in the superheated region. So from process 3 to 4, this is isentropic expansion in the turbine. So pressure will be dropped as well as the temperature, because heat energy or thermal energy will be transferred from working fluid to the blades of the turbine. So at state 4, we have the saturated vapor phase working fluid. So from process 4 to 1, as you can see Q out, so this is a condenser process. So this is a constant pressure heat rejection. So heat will be taken out of the working fluid with the help of condenser. So as the fluid moves from state 4 to 1, heat will be removed and the working fluid will be converted from saturated vapor to saturated liquid. So this is a cyclic process shown in the on the TS diagram, and this is the schematic diagram of ideal Rankine cycle. Then we have talked about the expression for to calculate the efficiency of ideal Rankine cycle. So here the expression of efficiency is work output divided by work input. So in the ideal Rankine cycle, the work input is in the form of thermal energy and work output is in the form of mechanical work through the turbine. So here two amount of work is input or output. So W's are two, that are the work produced by turbine and work consumed by compressor or pump. So WP is the work consumed by pump. So as it is a work consuming device, so that is a negative sign, and work producing device is a turbine. So W work turbine work is taken as positive. So W net is the difference of turbine work and pump work. So the efficiency of Rankine cycle is W net, that is W work done by turbine minus work consumed by pump. And Q1 is the amount of energy that is supplied in the process in the boiler through combustion. So Q1 is the amount of heat that is input, and the difference of turbine and pump work is the net work output. So the efficiency relation is Wt minus Wp over Q1. So in terms of enthalpy values for these process, so the turbine work is H3 minus H4, pump work is H2 minus H1, and Q1, that is heat supplied in the boiler, is H3 minus H2. So that is the efficiency when the pump work is considered. So in the TS diagram, from 1 to 2, this is a pump work. From 2 to 3, that is the heat energy supplied in the boiler. 3 to 4 is the turbine work produced, and 4 to 1 is the condenser heat rejection. So working fluid will be converted from saturated vapor to saturated liquid phase. This is a cyclic process. So efficiency of ideal Rankine cycle when pump work is neglected is shown here. So this is the efficiency relation that we have calculated in the previous slide. So H3 minus H4 is the work done by turbine. H2 minus H1 is the work consumed by pump. Whereas H3 minus H2 is the amount of heat supplied in the boiler. So if we neglect the pump work, that is H2 minus H1, then the relation is reduced to, that is the efficiency of Rankine cycle is H3 minus H4 and H3 minus H2. So in the numerical problem, in some numerical problem, you may be asked to consider the pump work, or it may be mentioned as the uh, negligible amount of work is done by the pump. Therefore, when you will be calculating the expression or value for the efficiency of Rankine cycle, then you will be neglecting out the pump work. So the reason why the pump work is neglected is that the expression for the work done for open system is W is equal to V dP. So I will write here. So the expression is W for, that is specific volume integration. So the integration sign is here, that is dP. So V P2 minus P1. So the value for, as in state 1 to 2, that is a saturated liquid, whereas in state 3 to 4 this is saturated vapor. So the value of saturated, for value for specific volume for vapor is given as Vg, that is much greater than Vf. Here the value for specific volume is Vf and here it is Vg. So as the difference is very large, therefore the value for Vf is very small and the value for Vg is very large. Therefore, when the in the pump work, so relation for pump work will be W pump will be equal to Vf into dP, or change in the pressure during the pump. So as this value is very small, so it may be in the region of 0.0001 2. So the value of pump work is very small. It may be 1 to 2% of Wt. So Wp is 0.02% up, maybe Wt. So as you can compare that the value of Wp is very small than Wt. That is the reason that pump work is, as you can see, that the value of work consumed by pump is very small than the work produced by turbine. Therefore, usually that pump work is neglected. Now we will discuss about the actual Rankine cycle. In the previously we were discussing the ideal Rankine cycle. Now we will discuss what happens in the actual Rankine cycle. So first of all, we will discuss what are the difference between actual and ideal Rankine cycle. So in the ideal Rankine cycle, the process of friction is neglected. So in the previous lecture, I have already mentioned that the fluid friction is neglected. So as the friction was neglected, so there was no pressure drop. So the pressure drop is zero in condenser and boiler, and the pipes are insulated. And also in the as the friction was neglected, so pressure drop in the pipe was were also neglected. So pipes were considered as the insulated pipes, and the process is considered to be adiabatic. So there was no heat loss to the surrounding. So this is a schematic diagram. So if you can see that the uh, blue line is shown as the so the cycle shown in the blue line is the ideal Rankine cycle, whereas cycle shown in the yellow is the actual Rankine cycle. So if you look more closely, you will see that there is a deviation in the line for ideal and actual Rankine cycle. So for example, here you can see that the yellow line is intersecting here, whereas blue line is here. So you will see that these are two different points, and it is evident here that blue line is above and yellow line is down, and here blue line is down and yellow line is above. So these are difference in the actual and uh, ideal Rankine cycle in the schematic diagram or TS diagram. So here in the ideal cycle, friction is neglected, pressure drop, and pipes are considered to be insulated and there is no heat loss to the surrounding. Whereas in the actual Rankine cycle, there are frictional effect present, and due to that friction, there will be a pressure drop inside the pipes, and also there will be a pressure drop in the condenser and a boiler. There will be heat loss from system to the surrounding. This will be a non-adiabatic process actual. So the reason the yellow and blue lines representing the actual and ideal Rankine cycle respectively. So these deviation one by one we will discuss all these deviation. What is the effect of that yellow line on the left hand side, top side, right side, and bottom side. So these difference or these deviation will be explored in detail in during this lecture. So these are the deviation, and in the ideal Rankine cycle, these are the straight lines, and in the actual Rankine cycle, the friction effect and other effects are included. So in the actual Rankine cycle, due to friction and other effect, the irreversibility is present in the actual Rankine cycle. Heat loss, friction, so fluid friction that comprises pressure flow or pressure drop uh, is the main cause of irreversibility. So in the Rankine cycle, irreversibility is present, and that irreversibility is due to friction, heat loss, and pressure drop. So losses in the actual Rankine cycle are the turbine loss and pump loss. So these two loss, turbine loss and pump loss, are due to the friction, fluid friction, and heat loss. Whereas the losses in the boiler and condenser are only due to the presence of friction, and the losses are the pressure drop in the boiler and condenser. So this is the same schematic diagram. So here on the left hand side, if you can see that the deviation in the blue and yellow line represent the losses in the pump. So pump loss is due to the friction loss as well as the heat loss. On the top above side, you can see this is a boiler process. So in the boiler, there is a pressure drop which is due to the friction. So this deviation is in the boiler. On the right hand side, this is a very evident deviation. This is in the turbine. So again in the turbine loss, this is due to the friction as well as the heat. And in the bottom, this is a condenser. So condenser loss is due to the friction. So there will also be a pressure drop in the condenser. So actual Rankine cycle. So the main component remains the same. So the first one is pump, second one is boiler, third one is turbine, and fourth one is condenser. So here I have already wrote the value for the pressure, temperature, and enthalpy at different states. So normally if we were talking about the ideal Rankine cycle, so first we will discuss the pressure, temperature. So here the pressure, temperature, and enthalpy value at state 1, at state 2, state 3, and state 4. All values of pressure and temperature are written. So normally if we were talking about the ideal Rankine cycle, then we know that in the ideal Rankine cycle, two are isentropic process and two are isobaric process. So the process 1 to 2 from pump is an isentropic process, and process 3 to 4 in the turbine, this is also an isentropic process. Whereas in the process 2 to 3, that is in the boiler heat addition, is a constant pressure heat addition, this is isobaric process. And for process 4 to 1 in the condenser, that is also constant pressure heat rejection in the condenser, that is also isobaric process when we were talking about the ideal Rankine cycle. But now we are considering the actual Rankine cycle. What happens in the real life, that the process 1 to 2 is not actually entirely the isentropic process. This there will be a slight deviation. So as you can see, slight entropy change. So for process 1 to 2 and 3 to 4, the pump and turbine respectively, there will be a little entropy change. And in the boiler, as you can see, I have already written on the boiler and condenser, there will be a pressure drop. So the pressure P2 is greater than P3, whereas if you looked in the ideal Rankine cycle schematic diagram, I have wrote that P2 is equal to P3, but in the actual there will be a pressure drop in the boiler and pressure will be reduced. And in the condenser as well, there will be also be a pressure drop. So P4 is greater than P1. So P4 is the pressure at the inlet of condenser and P1 is the pressure at the outlet of condenser. So due to some pressure drop, the value of pressure is written as P4 is greater than P1. So now we will be calculating mathematically the losses that are involved in the actual Rankine cycle. So the first loss was a turbine loss. So turbine loss comprises of heat loss as well as the fluid friction loss. So heat loss is the amount of heat that is rejected into the atmosphere because the turbine is not insulated entirely, and friction loss, or specifically if we are talking regarding the working fluid, then this is the fluid friction loss, that is actually a pressure drop. So to calculate, to check mathematically, so from second law of thermodynamics, the relation for the entropy change is equal to del S is equal to Q by T. So the value for the change of entropy is positive, and the del S universe is greater than 0. So in the practical processes, as you know that there are frictional effects present, therefore the entropy of universe will always be greater than 0. So as these are the ideal and actual process are shown on the TS diagram, so for the turbine the process is from 3 to 4. So the process 3 to 4 is a straight line. So one is a solid line and one is a dotted line. So dotted line is the process that represent the ideal process, whereas solid line is the process that represent the actual process. So as you can see that there is a slight deviation. So process 3 to 4 dash represent the actual process and process 3 to 4 represent ideal process. So here it is written that process 1, 2, 3, 4 and 1 represent the ideal Rankine cycle, and process 1, 2, 3, 4 dash and 1. So 4 dash represent the actual turbine process. So the work done by the turbine in the ideal case is H3 minus H4, and work done by actual turbine is H3 minus H4 dash, that is 4 dash. Therefore isentropic efficiency is the ratio of actual work done divided by ideal work done by the turbine. So here you should also remember that the efficiency is always less than 1 or 100%. If we are talking about in the percentage, then we should remember that efficiency will always be less than 1. So in the denominator we always put the value that is greater. So the work done by the turbine in the ideal case will always be greater than the work done by the turbine in the actual case. So here in terms of enthalpy we have written the value for the work done by turbine in actual and ideal case, and from that we know that the work done by turbine in the actual case will be less than the work done by the turbine in the ideal case. So the second loss involved in the actual Rankine cycle is the pump loss. So if we are talking about the pump, so the losses involved in the pump are heat loss plus friction loss. So similar to the turbine, the pump loss involved both these losses, heat loss and friction loss. Therefore, the entropy of the universe for due to the friction and other losses will be greater than 0. So if we look at the TS diagram, so process 1 to 2 represent the pump process in the ideal case, and process 1 to 2 dash represent the pump process in the actual Rankine cycle. So ideal 1 2 3 4 1 and actual 1 2 dash 3 4 dash 1. So here in the previous slide we have already discussed the 4 and 4 dash part when we were discussing the turbine loss. So in the current slide we have 2 and 2 dash here to represent the actual and so to represent the ideal and actual process. So work done on the pump in the ideal case is H2 minus H1, and work done on actual work done on the pump is H2 dash minus H1. So here we know that the pump is a work consuming device. Therefore, for ideal case, the work done on the pump is less, and in the actual case, the work done on the pump is greater, because pump is a work consuming device. So work consuming and work producing are opposite to each other. Therefore, work produced by ideal is greater, whereas work consumed by ideal device is less. So work consumed by pump in the ideal case will be less. So when we will be calculating the isentropic efficiency for the pump, then we will put the ideal work pump on in the numerator and actual pump work in the denominator. So in term of enthalpy, that is H2 minus H1 and divided by H2 dash minus H1. And we know that the work done on the pump work done on the pump uh, in the actual Rankine process is greater than work done on the pump in the ideal case. So now the third loss, that is in the boiler and condenser loss, is due to the piping. So due to the friction, pressure drop in the boiler and condenser occurs. So if we represent the from the TS diagram, we represent the ideal and actual Rankine cycle. So you can see that there is one solid line that is in the black color, and one is the dotted line that is in the blue color. So here the ideal Rankine cycle is a solid black line, whereas actual Rankine cycle is a dotted blue line. So in here on the left hand side, 1 to 2, you can see 1 to 2 is a ideal. So in the ideal Rankine cycle, it's the pump from 1 to 2, and from 2 to 3 this is a boiler, from 3 to 4 this is a turbine, and 4 to 1 this is a condenser. And similarly in the actual Rankine cycle, this is 1 to 2 dash, 2 dash to 3 dash, this is a boiler, so there is a pressure drop as well, so the dotted line is little beneath it. And from 3 to 4, 3 dash to 4 dash, this is a turbine work, and 4 dash to 1 this is a condenser heat rejection. So here this is in the condenser, you can see the pressure drop or piping loss as well. So the question arises that what are the process to increase the efficiency of Rankine cycle. So to we can increase net work done and thermal efficiency of a Rankine cycle by, so the first process is reducing the condenser pressure, and the second process is superheating to high pressure, and the third is raise the boiler pressure. So we will look into the detail one by one. What? So the first one is reducing the condenser pressure. So before going into the detail, in the previous chapter that we have studied was the chapter of exergy or available energy. So I have already told you the cyclic process is represented by an enclosed figure. So the area enclosed in the figure on the TS diagram represent the value of available energy. and the area beneath that enclosed figure and above the x-axis is the value of unavailable energy during the process. So if we look at the figure closely, if we want to increase the efficiency of Rankine cycle, then the first method is to increase the area of that enclosed figure. So on the left hand side it comprises the pump. On the top this is a boiler value, on the right this is a turbine, and on the bottom that is a condenser. So this is a low pressure line that is represented in the pink color. So the first method to increase the efficiency is to reducing the condenser pressure. So as you can see that this line is also a constant pressure line, as well as this is P constant. This is also a constant pressure line. I have written that as a PC, constant pressure line, and all the above lines are also this. The solid black line is also, and this dotted blue line is also constant pressure line, P1, P2. So as you can see that this pink line is down and this solid line is above. So the value for this constant is, that is a low pressure line, and that solid is a high pressure line. So to increase the area enclosed, so this is all, this is available energy. Area enclosed represent the value of available energy, and the area that is beneath here, so the dotted line, if we join these lines, that is unavailable energy. So if we reduce the condenser pressure, so some of that unavailable portion will be included in this available energy portion. So the second is the superheating to high pressure. So this red line represent the more superheated region than this black line. So that portion from the superheated region will also include in the available energy. If we raise the boiler pressure, so similar concept, lowering the condenser pressure and raising the boiler pressure means that we are including this portion of into the available energy as well. So all these methods are utilized to increase the efficiency of Rankine cycle. So there are two topics. Specific steam consumption is one. So we will just go through what is the meaning of specific steam consumption. So specific steam consumption is also known as steam rate. So it is defined as the amount of steam required to generate a unit power of turbine. It also represents the size of a power plant. So specific steam consumption, amount of steam required to generate unit watt power of a turbine. So as you know that the certain amount of steam exiting the boiler is entering into the turbine, and turbine blades are rotated by that transfer of energy from working fluid to the turbine blades, and turbine that blade that are connected to the shaft, and shaft that is connected to the generator produce electricity or work. So specific steam consumption relate to the amount of steam required to generate unit power of turbine. So specific steam consumption so acronym is written as SSC. So it is a steam flow divided by work net. So steam flow is given by kilogram per hour, and net work done by the turbine is in the kilowatt. So it is kg per kilowatt hour. So R here in the denominator is shifted to the denominator. So it is kg divided by kilowatt hour. So kilowatt hour unit is also kilojoules. So here, for example, it is written that in a steam power plant, the steam flow through the turbine is 500 tons per hour. So the 500 tons of steam is entering into the turbine per hour, and the amount generated, the power generated by the turbine is 100 megawatts. So here we are asked to find the specific steam consumption or steam rate. So specific steam consumption, so 500 tons are converted into kgs. So here it is 500 multiplied by 10 raised to power 3 kg per hour, and the power generated is 100 megawatt, that is converted into kilowatt. So that is 100 into 10 power 3 kilowatt. So when we solve this equation, the answer come out to be 5 kg per kilowatt. So if we want a turbine to produce 1 kilowatt in 1 hour, then at least we have to supply 5 kg of steam. 5 kg of steam to produce 1 kilowatt in 1 hour. So 5 kg of steam as moving through the turbine blade will produce equivalent to 1 kilowatt hour. So that is a specific steam consumption. So the next topic is heat rate. So heat rate is the heat input required to produce unit shaft output, that is 1 kilowatt hour. So heat rate, so amount of heat added is to the boiler. So heat rate is equal to Q1 divided by W net. Q1 is the amount of heat that is supplied through the boiler. And also thermal efficiency is given by W net over Q1. So heat rate is the reciprocal of thermal efficiency. And also heat rate, the unit of Q1 is kilojoule per second, whereas when we are talking about Q1 in the term of heat rate, the unit of energy supplied is given in the form of kilojoule per hour. So here we have converted the second relation into R, so we have multiplied it with the 3600. So 3600 Q1 over W net, and the Q, the unit of here, in if we are using this 3600 relation, then the unit of Q will be kilojoule per hour and W net will be in kilowatts. So if we are talking about in terms of efficiency, then the relation of heat rate is 3600 divided by efficiency, thermal efficiency, and the unit will be kilojoule divided by kilowatt hours. So the conceptual question answer: a refrigerator in room or kitchen uses the refrigerant are 134 and the temperature ambient is 20 degrees centigrade. And if you want to make ice cube at minus 5 degrees centigrade, what is the minimum high pressure and maximum low pressure it can use? So here we have asked the high and low pressure. So you know that the high pressure is provided in the compressor and low pressure is provided in the evaporator. Since R134 must give heat transfer out to the kitchen air at 20 degrees centigrade, it must be at least uh, be that hot at state 3. So if we are talking about the refrigeration system, then we have a compressor, then condenser, then expansion valve, and then evaporator. So the condenser process occurs, so amount of heat rejected to the ambient air, the temperature of ambient air is 20 degrees centigrade. Therefore, against the, if we look at the properties of refrigerant R134A in the table B5.1, then the saturation pressure is 573 kilopascal, that is the minimum pressure. And freezer, so the evaporator is at the minus 5 degrees centigrade, and the if you want ice to produce ice at that state, then the pressure is further lowered down, and the pressure at the evaporator against the minus 5 degrees centigrade is 245 kilopascal, that is the maximum low pressure. So how many parameters are needed to completely determine the standard vapor compression refrigeration cycle? So there are two main parameters, two high pressure and low pressure. The high pressure and the low pressure. This assumes the exit of the condenser is saturated liquid and exit of the evaporator is a saturated vapor. So uh, in the condenser heat is ejected to the ambient, whereas in the evaporator heat is absorbed. So when the heat is rejected in the ambient, then the refrigerant is converted into saturated liquid. Whereas when the heat is absorbed in the evaporator, so refrigerator again gains the heat and the phase is changed to the saturated vapor. So if the steam power plant is running on a Carnot cycle, name the fourth process. So steam power plant is not run on the Carnot cycle, and it runs on the Rankine cycle. And the process involved in the Rankine cycle are isentropic compression in the pump, isobaric heating in the boiler, isentropic expansion in the turbine, and isobaric cooling in the condenser. So home assignment for the current lecture is, you should, all students are advised to go through example problem discussed during this lecture. So you must go through your textbook and explore all the example problem and the problem in the exercise that are uh, connected to the topic discussed during this lecture. And you should write the handwritten lecture summary report and send it to my email ID. And you should also prepare this lecture thoroughly, as there will be a viva or an oral questions session for every student. Thank you very much. Allah Hafiz.